Happy New Year, everyone, and welcome to part 21 of the lecture on designing organic syntheses. Subject of today are carbon frameworks which resemble polyhedrons. Most of what I will tell you today is nicely presented in the marvelous book of Henning Hopf, Classics in Hydrocarbon Chemistry. And first of all, let's talk about the so-called prismanes. So, a prism, how does that look like? So, this is a drawing of a prism, and if this is meant as the structure of a hydrocarbon, then this is prismane, and especially this is the 3-prismane. Closely related is this structure, a cube, and this cube, well, straightforward name of that hydrocarbon would be cubane, and well, but nevertheless it is also a prismane, the 4-prismane. There are, of course, even more prismanes. What about the 5-prismane? So drawing becomes a bit more complicated. Like this, and well, I won't draw the 6-prismane. We'll just write that down. That we can now have a look at the steric strain energies. Of each molecule. 320, is that right? kcal per mole for the 3-prismane. While at 90 degrees, it has a half-time of about 11 hours. But it is well, stable, completely stable at room temperature, even though it is that highly strained. Strain energy of cubane, 172 kcal. It withstands higher temperature up to 200 degrees. So also stable until 200 degrees. Well, and the 5-prismane, 144 kcal. This is the most stable of all prismanes, with a 6-prismane and even more with a 7-prismane. The strain energy goes up again. here we have 164 kcal. In all of those of the syntheses that have been planned and have been performed for these structures, one of course had the idea you have to put in somehow the energy. You can do that if you have intermediates on a high energy level like carbines, or you put in photo energy. Photochemical reactions are regularly very important for synthesizing this type of products. So, if we have a look at that 3-prismane first, and as I said, at 90 degrees, it has a half time of about 11 hours. What will be the product of rearrangement of this compound? Well, it is an isomer simply of benzene. And indeed, it reacts to give benzene. In fact, the original name of the 3-prismane is the Ladenburg, or better Ladenburg, benzene. Since the chemist Ladenburg suggested in the year 1869 that this is the structure of benzene. So he was wrong, but nevertheless, Ladenburg benzene is well, symbolizes the high interest into this isomer of benzene. So, it has been synthesized by the group of Katz in 1973 at the Columbia University in New York. Well, we don't do a retro synthetic plan in that case because we wouldn't get the idea. Some strange reactions have been applied there. They found some interesting reactions forming highly strained molecules and then thought, well, maybe we could start with these strained molecules and build an even more strained one, the Ladenburg benzene. Okay, so the Katz group started with cyclopentadiene, treated that with methyl lithium, and it's clear what will happen. Methane will be formed, and of course the aromatic cyclopentadienyl anion with the lithium counter cation. Then dichloromethane is slowly added in, dry dichloromethane, of course. Lithium chloride is formed. And this highly sensitive compound. Treating that at low temperature with a second equivalent of methyl lithium. Once again, methane is formed, and once again, second equivalent of lithium chloride. And as a main product, this one. The yield obtained 45 plus minus 5% yield. We did it a lot of time, and the maximum yield was 59%, but obviously achieved only once. So, this is also a highly strained molecule. It has a trivial name called Valine. While in the original publication they didn't make any remarks about the mechanism of its formation, while later on another group, I think from Italy, had a publication in Tetrahedron Letters where they discussed mechanism based on some experiments with certain C marked frameworks. And well, I think the best explanation might be that, well, whatsoever we get as an intermediate this carbene and the carbene undergoing a cheletropic reaction which reminds us of a Diels-Alder reaction with this as the diene and that as the dienophile. Okay, just a suggestion explaining at least the structure. So, let's call that BV as abbreviation for Valine. This Valine is next treated with this electrophile with this diazo functionality. This is a diazo dicarboxylic acid imide, phenyl substituted. Well, this is well known as a very electrophilic dienophile. In this case, it will interact with the Valine, and an intermediate like this will be formed first. With dipolar intermediate, then a lot of rearrangement steps will occur these steps are outlined in Henning Hopf's book, but well, you just can't keep that in mind. So I just write down the final result of the rearrangement. It's this one, and you see the only thing we still have to achieve is forming that bond and get rid of that stuff there. Well, astonishing 60% yield of this product was obtained. Then hydrolysis, and secondly oxidative workup with well, copper chloride as the oxidant. Delivers this azo compound, and the final step is photochemical radiation. Molecular nitrogen is formed, and the corresponding diradical, which combines, forming that final CC bond. Okay, they get hands on that compound, but for these last steps, just between 4 and 6% yield were obtained. So let us then have a look at this special hydrocarbon, cubane. Well, it not only resembles a polyhedron, but the specialty is that all sides are, all planes here are equal. So it is a completely regular polyhedron, and complete regular polyhedrons are called Platonic solids. So this is one example of a Platonic solid. Well, another one is, of course, the well, a dodeca. Well, we call it a dodecaeder, and dodecahedrine. So this is cubane. Dodecahedrine is the hydrocarbon with which is also resembling one of the Platonic solids, having 12 5-membered rings, so pentagons. 12 pentagons in a complete sphere. Well, forming a C20 H20 cage. So, and of course, now the complicated part for drawing these structures begins. We will try that. So first pentagon. Here the second one, third one. And behind the blackboard, another one. So here we will have a pentagon, there a pentagon, and now we have to connect these positions. Well, so it should be complete round, yeah, but ball shaped, but well, I think you get the point, okay? So we will later on talk about the synthesis of dodecahedron. First of all, let's discuss cubane. So as you already might know, Eaton's group synthesized cubane. So, and one important, rather important intermediate is this one. And as an exercise, please just figure out in 1 or 2 minutes how did they synthesize that one. So every one of you noticed that this is obviously a product of a Diels-Alder reaction. A Diels-Alder dimerization of this bromo-cyclopentadienone. And as you might know, normally those cyclopentadienones are not stable, with the exception of highly substituted ones. For instance, that so-called tetracyclone with 4 phenyl group, which itself is then known. So these should be phenyl groups for Diels-Alder reaction, losing carbon monoxide and resulting in the hexaphenyl benzene in high yield. So that means this is so sensitive, it reacts to polymers plus that Diels-Alder product. You can't buy that, you have to generate that in situ. So you might do that by an elimination reaction. Best idea is treating this tris-bromo cyclopentanone, for instance, with the base triethylamine has been applied. So 2 of those bromines you can introduce by a simple addition reaction of elemental bromine to the double bond, and this bromide in allylic position you can introduce with the well-known method N-bromosuccinimide under radicalic reaction conditions with the radical reaction starter. So, now back to this structure. Let us draw this one in another perspective. Then we notice that this double bond is in close proximity to that one. And therefore, a photochemical 2+2 cycloaddition reaction has been tried. It is successful. I started once again. No. Yes, this is the result. Okay. So you see, cycloaddition process forms a four-membered ring. At the same time, also here, a four-membered ring is formed. One four-membered ring and the second one. So we now need a ring contraction. And we know as an example for ring contraction the so-called Favorsky rearrangement, for which we need ketones, cyclic ketones, with a halide in alpha position. We already have that here. Yeah? And that means, in this case, simply treating it with KOH in aqueous solution. Will form the cubane dicarboxylic acid in about 30% yield. And this reaction has been performed in medium scale up to 2.7 kilograms of that product formed in a one-pot reaction. So from here, once performed, 2.7 kilograms. Well, a couple of more steps then will lead to the cubane. So, let's go on with dodecahedron. First, that molecule was synthesized by Leo Paquette's group at the Ohio State University. I think it's Ohio State. And this is a somewhat tedious step-by-step approach. On the other hand, more elegant is the synthesis by Prinzbach from Freiburg University. So first of all, the basic idea of his synthesis. He thought that this would be an interesting starting compound. Well, okay, you see here we have a 5-membered ring. There also 5-membered ring. And then, well, these methylene group here, a CC single bond connecting the two 5-membered rings. Here a methylene group, there a methylene group, and in the center we have a 4-membered ring. So, unfortunately, we have to draw that again symmetrically to the plane of that 4-membered ring. So it wasn't that complicated. This structure he called pagodane, and he noticed that this is far more strained than dodecahedron. Dodecahedron is not that strained. So we have a lot of strain energy in here. And if we could connect these two carbon atoms, therefore we have to get rid of 1, 2, 3, 4 hydrogens. And we have to put these 4 hydrogens in here, using them to cleave this CC bond and that CC bond. Yeah? Then, well, we have dodecahedron. This is an isomer of dodecahedron, and he hoped for a rearrangement reaction similar as it was the case, as you certainly remember, for the adamantane synthesis of Paul von Raag-Schleyer. Well, we tried it. We tried it a lot of times, and well, always got a horrible mixture and painfully isolating than dodecahedrine. And then up to 8% yield, then using palladium on aluminum oxide and, of course, heating that up. Well, a better yield of the dodecahedrine skeleton, much better yield, they achieved than adding one equivalent of bromine to that single bond. Of course, it's symmetrically, or that. That means we have cleaved the central four-membered ring. We leave out the other stuff that is around there. Having this dibromide, then treating that with zinc, having then two olefins. Okay? Cyclopropanation gave this structure with missing that and that single bond and having a cyclopropane here and a cyclopropane there. And then again, similar reaction conditions, a far better rearrangement took place, forming then dodecahedrine with dimethyl. Dodecahedrine with approximately 30% yield. So, nice synthesis. However, we now have to talk about the problem where to get the pagodane from. Okay? There was an additional interesting idea. They started with a Diels-Alder reaction of this hexachlorocyclopentadiene and norbornadiene forming this strange product. This was already known, this compound. Isodrene, and it was I think in the late 60s, a very well-known insecticide produced in very large scale. Again, in Diels-Alder reaction, Now with that double bond here, losing SO2, since benzene ring is formed then here. So, and now you already notice that rather nicely one part, the bottom part, or the upper part, just it's a choice, of the pagodane is already established. Sorry, nope. There's a mistake. This is formed after the Diels-Alder reaction, and SO2 is evolves, making that diene. Actually, I'm not quite sure anymore. Has this been isolated at all? Because now a very interesting reaction occurs, a concerted process, where these two hydrogens jump to these two carbons, and the aromatic system is the result. So, okay. Luckily, we don't need to go on in writing down all those chlorides, because in the next step, just with lithium in tertiary butanol, very nice, almost clean reaction leads us to the corresponding hydrocarbon. This one. And then, similarly, in a few reaction steps, again, with this diene, the Prinsbach group succeeded in setting up the second benzene moiety. These two benzene rings are completely parallel. And as I told you before, photochemical energy, photoenergy, is a nice way to get energy into that molecule to build up highly strained systems. And a photochemical 2+2 cycloaddition reaction is possible it's an equilibrium The four-membered ring is formed. Resulting in this structure. And another very interesting step follows. Again, it yields all the reaction, now with the well-known dienophile maleinic acid anhydride. It's in this case an axo Diels-Alder reaction, because ando doesn't work here. Yeah, so an axo Diels-Alder reaction with this diene forming the olefin here, and this olefin then undergoes at the same time again a Diels-Alder reaction as dienophile with this diene. So what will be the result? Well, okay, not bad. Okay, like that. Well, so we now know what this looks like here. We will abbreviate that. Oxidatively, one can get rid of this one. Having now that symmetrical setup, okay. So, what do we need? We have to eliminate one carbon on each side. We just need a methylene bridge and not an ethylene diol bridge. This has been achieved in a multi-step process. First, hydroboration. Secondly, oxidative workup. So, hydroboration twice, oxidative workup. Then you have an alcohol functionality here and an alcohol functionality there. I don't think that there is any selectivity in terms of those stereo isomers. But it doesn't matter for the synthesis because we make an elimination reaction later on. So, having two hydroxyl groups, alcohol here, alcohol there, then it is oxidized. At that time, they used that oxidation with chromates. Today we would use a tempo oxidation or something like that. And after two carbonyl groups have been established, in the fourth step, then diazo groups are introduced. No, wrong. You've noticed that already, right? So, photochemically, in methanol, a so-called Wolff ring contraction occurs. After a while, it's not that difficult anymore to draw these types of structures. So, and as you see with some other methods, one is then able to get rid of the ester functionality to get to the final dodeca, to the pagodane, and then the rearrangement to the dodecahedrane in the last step with about 8%. So, well, what did they do with the dodecahedrane? They, of course, measured NMR spectra, right? Yeah, we would also do so, clearly. Yeah? So, proton NMR, one singlet at 3.38 ppm. That's it. It's highly symmetrical. It has only one sort of CH bonds. The dodecahedrane, not the pagodane. Okay? The dodecahedrane. And also certain C, NMR, one signal at 66.9. Well, okay, enough about the dodecahedron. For the program of today, I have one more molecule. And I think we should start with a retrosynthetic analysis of the 1,1,1 propylene it's this. So just think about for a few minutes, how would you disconnect here? So you should have noticed that this is indeed a very special molecule from the geometry, bond geometry at those carbons. There is no hydrogen sitting here and there. Otherwise it would have 5 bonds. Okay, so, but all carbon-carbon bonds here, 4, have the same direction, like an umbrella. Okay? So-called carbons with inverted bond geometry. Okay? So, and in retrosynthetic analysis, we could think of, well, let's call that R1. Disconnect in the center homolytically to a diradical like that. Actually, under certain moderate conditions, this is a stable molecule. You can keep that for a while, but it has the tendency to polymerize via such diradicals or with a nucleophile, butylithium. Butyl group there, lithium there, and then polymerization. Yeah? But forming this bond, well, a long time it was a matter of debate. Is there a real bond here, or does it have diradical character and is somehow with sterical hindrance or so on stabilized? Yeah? Actually, it is clarified, but I'm not quite sure what is the result. They have an X-ray structure analysis, and it is a very long central bond here. So this didn't turn out as the retrosynthetic analysis of choice. Far better is, well, let's get rid of 2 3-membered rings. Just leave 1 3-membered ring. Leaving group here, leaving group there, and having twice donator reactivity. Well, not simply by deprotonation. Well, we would have to make metal halide exchange, double metallation. From something like that, metallation. of course, maybe stepwise. Well, and this, just adding a carbene to the olefin. So, and indeed at Munich University, group of Professor Simes did that synthesis with XR chlorides, making use of bromofoam, basic medium, getting a 45% yield of this, and then just treating that with dropwise addition of N-butyl lithium at minus 50 degrees, 34% yield of that 1,1,1 propylene was obtained. In the next lesson, next Tuesday, we will again talk about synthesis of synthesis of hydrocarbons, but these hydrocarbons are natural products. Then, well, thank you for listening for today. See you next week, Tuesday.